Welcome to the Deep Dive. We're the ones who dig through all the noise to find those nuggets of insight for you.
Glad to be here.
Today, we're jumping into large language models, specifically how they reason, or maybe how we can teach them to reason better.
Right, and we've got this really interesting research paper as our guide. It's called Reinforcement Learning for Reasoning in Large Language Models with one training example.
One example, that title alone grabs you.
It really does. And that's basically our mission for you today, to unpack this idea, this surprising finding that maybe, just maybe, you don't need mountains of data to teach an AI to think logically.
Even just one piece of data might do the trick.
Potentially, yes.
Yeah.
A very specific piece, but yes. It challenges a lot of assumptions.
Okay, let's set the stage then, because the standard thinking, the way it's always been done is that these powerful AI models, they need massive data sets.
Absolutely massive. We're talking huge amounts of text, code, whatever it is. The more data, the smarter the model. That's been the mantra.
Especially for complex things like mathematical reasoning or logical deduction, you'd assume that takes tons of examples.
Precisely. You'd think you need to show it countless problems and solutions. So the core idea in this paper, it's pretty counterintuitive.
It goes against the grain. So what is this big, unexpected finding?
They discovered that using a specific technique, it's called reinforcement learning with verifiable reward, or RLVR for short.
Okay, RLVR.
They could get huge improvements in the reasoning skills of these LLMs using, like the title says, sometimes just one single training example.
Hold on. One example that just sounds wrong based on everything we hear about AI training.
It does. It really makes you question things. Are we just throwing too much data at the problem sometimes?
So how did they even figure this out? What was the experiment like?
So the main focus was on this specific model, Qin 2.5, Math 1.5b. It's a model already decent at math.
Right.
And they applied this RLVR method. But instead of the usual giant data set, they fed it just one carefully chosen math problem to learn from.
And what happened? Did it make any difference?
A huge difference. It was pretty dramatic, actually. On the standard benchmark, Math 500.
Yeah, I know that one. Tough high school math problems.
Exactly. The model's accuracy went from 36%, which is okay, but not amazing,
right,
all the way up to 73.6%.
Wow. Just from that one example, it more than doubled its score.
Pretty much doubled it, yeah.
Yeah.
And it wasn't just on Math 500. They looked at average performance across 6 different math reasoning tests.
Yeah,
same story. Jumped from about 17.6% average accuracy to 35.7%. Again, more than double.
It's hard to wrap your head around.
Yeah.
One single problem did all that. How does that compare to using, say, a larger data set?
Okay, this is where it gets even wilder.
Yeah.
They also trained the model using a set of 1,200 examples.
Okay, 1,200, that sounds more typical.
Right. And crucially, that set of 1,200 included that one special example they tested on its own.
Ah, okay. So what happened? The 1,200 must have been way better, right?
Nope. The performance they got with just the single example was essentially the same as the performance they got using all 1,200 examples.
You're kidding? One example did the work of 1,200.
Pretty much, yeah. And get this. When they tried using just 2 specific examples.
Let me guess, it was even better.
Just slightly better than the single example in the 1,200 examples. Match 500 went up to 74.8%, average to 36.6%.
2 examples beating 1,200. This is really messing with my understanding of AI training. Was this just a one-off thing with that specific Quen model?
That's what they checked next. And no, it seems pretty robust. They saw similar big gains with other models, too.
Like what?
Like a bigger version, Qin 2.5 Math 7b, and models using totally different architectures, like Llama 3.2, 3B Instruct, and also a distilled model.
So different sizes, different families of models?
Yeah. And they also tried different RL algorithms, not just GRPO, which was their main one, but also PPO, another common one. Same kind of improvements.
Okay, so this seems like a real phenomenon, not just a fluke. You mentioned these specific examples, Pi 1 and Pi 13.
1 and 13. Those are the 2 single examples that gave these really strong results in their tests.
What were they like? Were they incredibly complex, obscure problems?
That's the surprising part. Not really. One was basically an algebra problem dressed up with a bit of physics.
Okay.
It involved wind pressure on a sail. Using a formula P equals KAV cubed, you had to figure out the wind speed.
Sounds solvable, at least for a math-focused model.
Exactly. And 13 was a geometry problem.
Yeah.
Finding the equation of a circle passing through 3 points, then something about a line intersecting it. Again, standard-ish geometry.
So not some weird edge case problem that magically unlocks everything.
It doesn't seem like it. And what's really interesting about it, the algebra one, The paper notes the base model before any RL training could almost solve it.
Oh, really? So it wasn't completely clueless?
No, it got most of the steps right.
Yeah.
It mainly tripped up on the very last calculation, which involved finding the cube root of 2048.
Ah, the final arithmetic.
Yeah. The model spat out different answers for that cube root, like 4, 10.95, 12.6992, 13, all over the place. Interestingly, it often said 12.7 or 12.7, which is super close.
Yeah.
The correct answer in the dataset was 12.8, though the actual value is closer to 12.7.
So it was right there, just needed a nudge on the final calculation. What about 13, the geometry one?
Similar story. The base model had some partial success with that one too, even before training.
So these magic examples weren't magic because they were impossible, but maybe because they targeted a specific weakness, the model was close to overcoming anyway.
That could be part of it. It's like they were perfectly poised to push the model over a threshold. It's still kind of amazing how much improvement they triggered.
Definitely. But the story doesn't end there, right?
Yeah.
You mentioned some other weird or fascinating phenomena, something about post-saturation.
Yes, post-saturation generalization. This is really mind-bending. So the model trains on that single example, 1 or 13, and eventually it gets really good at that specific problem. Its accuracy on the training example hits close to 100%. It's basically saturated. It can't get much better at solving that problem.
Okay, makes sense. It learned the lesson.
But here's the weird part. Even after it hits that ceiling on the training example, its performance on new unseen test problems keeps going up significantly.
Wait, so learning the training problem perfectly isn't the end goal. It keeps getting smarter overall even after it seems done training.
Exactly. It keeps generalizing better to problems it's never seen, long after it has seemingly mastered the single example it was trained on. This happened with both 1 and 13.
That is not what I'd expect. Usually you worry about overfitting, where performance on new stuff gets worse once it memorizes the training data too well.
Right, and they know this is different from what often happens with larger datasets where test performance might peak or even decline as training accuracy maxes out.
Very cool. What else did they see? Something about gibberish.
Yes. This was another strange observation. In the very late stages of training on the single example, the model started to, well, overfit in a bizarre way.
How so?
For that one specific training problem, it began producing outputs that the researchers described as unintelligible, multilingual gibberish mixed with correct solutions.
Gibberish, like it just broke.
It sounds like it. But, and this is crucial, while it was spewing nonsense for the training problem, its answers and reasoning on the unseen test problems remained totally coherent and strong.
That's incredibly weird. It's like it was sacrificing its performance on the known problem, but still improving on unknown ones.
It's a very strange pattern, almost like it learned the lesson so well it started, experimenting wildly on the known problem but kept its composure for new challenges.
Bizarre. Okay. Any more surprises?
Yep. Cross-domain generalization.
Meaning?
Training the model on a single problem from one area of math, like the geometry problem 13, actually improved its performance in other areas of math it wasn't explicitly trained on, like algebra or number theory.
So learning geometry made it better at algebra. That kind of transfer isn't always guaranteed.
Not at all. But they saw it happen. Learning from one specific domain seemed to boost reasoning skills that were applicable across different domains.
That suggests it's learning something deeper than just the solution to one problem.
It seems that way. And one final observation tied to that. They noticed the model started using more self-reflection terms in its answers on the test data.
Self-reflection? Like what?
Words like rethink, recheck, recalculate. These started showing up more frequently in its reasoning steps on the test problems as the one-shot RLVR training went on.
So it's not just getting more answers right, it's actually showing signs of being more careful, more deliberate in its process.
That appears to be the case. It's exhibiting behaviors we associate with more careful reasoning.
Okay, this is all incredibly fascinating, but why? Why does training on one example work so well? What's the mechanism?
Right, the million-dollar question. What's actually happening under the hood?
Yeah, what's the magic ingredient here?
Well, the researchers point primarily to the policy gradient loss component of the RL algorithm they used, GRPO.
Policy gradient loss.
They argue that's the main engine driving these improvements. It's about reinforcing the actual steps, the policy, that lead to the right answer. They also make a point to distinguish this from another known phenomenon called grokking.
Grokking. That's when a model suddenly gets something after ages of looking like it's not learning, right? Often linked to things like weight decay.
Exactly. They're saying this RLVR effect is different, driven more directly by the reward signal shaping the policy, not just regularization slowly finding a general solution.
So the RL part, rewarding the right kind of thinking steps, is key. You also mentioned exploration earlier.
Yes, that seems really important too. They found that encouraging the model to explore different potential reasoning paths actually helps.
How do they encourage that?
By adding something called an entropy loss to the training objective with the right weighting. Basically, it gives the model a little nudge to not always take the most obvious path, to try out alternatives.
So it's like, don't just stick to the one way you know works, try other ways too.
Sort of, yeah. Keep the options open, be a bit more diverse in your approach, and doing that, adding this entropy loss, boosted performance even further.
Okay, that makes some sense. Reinforce the good steps, but also encourage trying new things.
But here's the kicker, another bonus finding. They tried applying only the entropy loss. No reward for getting the right answer on the training example. Just the nudge to explore different reasoning paths.
Just exploration for exploration's sake. What happened?
It still significantly boosted performance. Just adding entropy loss alone without any outcome-based reward gave a big jump on Math 500. I think it went up to 27% accuracy from the baseline, just with that.
Wow. So simply encouraging the model to think differently, even without knowing if it's right, makes it better at reasoning.
It appears so. It really shows how complex these learning dynamics are.
Yeah.
Maybe just forcing it out of its default rut helps unlock latent abilities.
This has huge implications, doesn't it, for how we pick training data, maybe?
Definitely. If one example can do this, which examples are best? How do we find them? And it also tells us a lot about the capabilities already sitting inside these base models, just waiting to be unlocked, perhaps.
Absolutely fascinating stuff. Okay, so let's try and wrap this up for everyone listening. The huge takeaway, the headline, is really the surprising power of this RLVR technique with incredibly minimal data.
Right. One example, maybe two, challenging that whole bigger is always better idea for training data, at least for boosting reasoning.
Then we saw these really intriguing side effects, these phenomena like post-saturation generalization.
Where it keeps improving after mastering the training data.
The weird overfitting gibberish on the training task while staying sharp on tests.
Yeah, that was bizarre.
Cross-domain transfer, and the increase in self-reflection language. It points to something deeper happening.
For sure. It's not just about getting the answer right.
So for you listening, the provocative thought here is, if one or two examples can unlock so much reasoning potential, what does that say about what these models already know or are capable of? How much latent ability is just sitting there?
And what are the truly best ways to tap into that? Is it about finding those golden examples? Is it about encouraging exploration, like that entropy loss finding suggests?
Loads of open questions remain. The paper itself mentions needing to understand optimal data selection for RLVR better, figuring out this post-saturation thing more deeply, understanding the role of entropy.
Yeah, lots to dig into still.
But hopefully this deep dive has given you a solid understanding of this cutting-edge research, a shortcut to being informed, and maybe sparked a few aha moments about how AI might learn to think.
We hope so. It's definitely made us rethink a few things.